All right. So welcome back. Hope you enjoyed the class on Monday. We tried something new. I'm gonna at the end of the class ask, like end of the quarter, ask you how did you like the guest, lectures. We might have also a guest lecture from industry later on, probably in week 10. Still, I'm trying to figure out the details, but would be someone from AWS, who's working on security of AWS, who might join us, or someone from autonomous, Toyota and security of cars and vehicles and autonomous driving. Or maybe someone else. Let's see. But yeah, so we talked about side channels. If there are questions about side channels, feel free to ask on CampusWire. But I'm pretty sure that Justin did a great job on presenting what he was working on. So plan for today is that we're gonna do the presentations first. And then based on the time that we left, I'm gonna finish the discussion on sensor security. There's a few more things I want to discuss, kind of especially connection between sensor security and machine learning. And then next week we're gonna start a new topic. So we're gonna talk about that. So a few things about presentations. For the groups that are coming here, so we're gonna start by the paper 1 and then 2, 3, and so on. So once you're coming here, when you're presenting, there's like usually 3 or 4 of you. The person who is talking, it's better to stand here because the microphone is here. The other people could one person here and the other 2 that are there, and then you can switch. So whoever is speaking, it's better to be here. Don't speak on that side because usually that doesn't, capture very well with the microphone. So make sure that you switch. Try to stay in 10 minutes. Another thing that I found very not very user friendly is like people coming with their phones and trying to kind of read their notes from their phone. That's not a good idea to do. If you have notes, either at least put it here and then kind of like occasionally look at it. Try to be kind of a little bit more interactive, right? And generally don't try to kind of like mechanically just read from a script. Try to actually speak and connect with the audience in general. And then in order to present, this is the Zoom link, same Zoom link that we use for the class. One of you who's presenting, just join the Zoom link and share your slide. Disconnect your audio, just share your screen so that we can put it on the screen so everybody can watch it. Another thing that I want you to do is that if you go to the class website, you will see that there is this folder here called presentation files. Please upload your slides in PDF format there. Name it just G11, G12, and so on. So you don't need to add your name, just the paper number. One person, please just upload it there. The reason for this is that other people who wants to look at your slides, they can see it. It's useful for the exam and for reviews and all. Okay. So for the people in the audience, multiple things you should do. The most important one is to listen because the whole point of the presentation is for you to learn something new. We're going to talk about specific sensor security attacks today, which are kind of continuation of what we discussed last week. So you're going to actually see a little bit more detailed attack and a little bit more specifics of each attack. These are also neo attacks, and I try to make them different from each other. So it's like different modalities. You will see deep fake attacks on voices. You're going to see like underwater attacks. You're going to see laser attacks and so on and so forth. There's a wide variety. So it's actually quite interesting in terms of different types of attacks that they can see. I think all of them except one are attacks, and then one of them is defense, if I remember correctly. The reason is that generally like attacks for sensor security is generally a little bit more interesting. But of course, at the end of the day, you have to come up with defenses. But as you're listening to the presentations, also think about your projects. This could be a good place for your projects. The second thing that you should do is asking questions. You can ask questions during the presentation or at the end of the presentation. The more interactive the kind of discussions are, the more interesting the presentations will be. And the last thing is doing this review forms. So if you go again to the website, you will see that there is a link for review form. If you open it, it's a Google form. At the beginning of the class, I told you that we're going to use Perceptive, but I played with it a little bit and saw that it's like too much and lots of things that I didn't like. So I'm just going to go with like a very plain and simple review form. So who has to submit this? Whoever presenting today. So groups 1, you have to listen to others' group presentation and submit this. And groups 3. So whoever is in group 3 has to submit this. Group 2 and 4, you don't need to submit. You have to submit it for each presentation. So all the 5 presentations. You will submit it per group, right? So you're not individual, you submit it per group. So the way it works is that you put your name here, the paper number that you're reviewing, and then there are like 4 questions, simple questions. The first question is about the content. There are these 3 questions, each one 10 per 10 points. Select a number. Also presentation skills, 3 questions, read them and then answer them. And critical questions, also the same. And then engagement and Q&A. Just kind of like, if there is no Q&A, that's fine, give them the points. This one is 5 points each. And then the last thing is give them some constructive feedback. Don't give them like great or well done or things like that. Maybe like a few sentences. Try to be respectful and give constructive criticism if there is any. And again, since it's for the entire group, you can single out different presenters, but just generally goes through the whole group. So the whole group is graded. And then once we have these, I'm gonna share it with the presenters at the end of the week. You have a week to do this, but those of you who are in class, you probably want to do it as we are going, so that you're done with that part. Any questions about the reviews? Yeah.
Yeah, so for like discussions during the presentation, is that included in the 10-minute limit?
No, so the presentation itself 10 minutes, and then if there are questions, you can add to that. Yeah. But I mean, like 1 or 2 minutes here and there, that's like 8 to 12 we are gonna accept. Yeah.
So can you clarify the who's reviewing who's like your group 1, you review the other 4 or the 2?
Yes, so if you're like every person that presenting today, review every other groups, all the other groups.
Okay.
And then everybody who's presenting in group 3, so all the group 3 papers, again, also reviewing your presentation.
You're reviewing group 1 for every other week, group 2 reviews for only, or is it?
Yeah, so 1 and 3 together and 2 and 4 together.
Oh, gotcha.
Does that make sense? So there is like paper number 1 to 5. There is G and there is like 1 to 5. So all the people in G1, which is paper G11, G12, G13, they have to review each other. And all the people in G31, G32, G33, G34, G35, they also have to review G11, G12, G1. Okay? Yeah. Say it again.
If I submitted, does it count for my entire group?
If you no, it's in this part is individual. Yes. Yeah.
So each person is doing 9 reviews?
Doing 9 reviews. Yes. I'm assuming like I think the first group is 6 papers. Yeah, but yeah, 9 or 10.
Do we review ourselves?
You don't review yourself. Yeah. I mean, you are here, right? So. Yeah.
It's like that mapping of like 1, 2, 3, 2 to 4 online somewhere.
Say it again.
It's like the mapping of like 1, 2, 3, 2 to 4 online, like you have there.
Oh yeah. So I mean, if you go to the schedule. Oh, okay. So you see this kind of this. These are 1, 2, 3, 4, and these are paper numbers. So essentially, everybody in this row, all the names will review every presentation today. So the wall will review this group and then group the 3rd and 4th. And then everybody here will also do the same. So we'll review everyone today. Okay. So Vincent and Ishan and so sure. You're actually Ishan, right? What's your name? Audrey. Okay. So yeah. Does that make sense?
Yeah.
And then you have a week, so if you're not doing it today, you can do it, you can watch the lecture and do it. We good? All right, so fairly complex strategy. All right, so can the first group come up?
We're team two.
All right.
Just join the Zoom.
Yes, yeah, join the Zoom, join the Zoom. And if you want to put it here.
Yeah, that'd be cool.
Yeah.
I don't believe in sticker notes.
No, you still do.
Stop sharing.
What?
Say 810-882-955. Oh,
Oh, yeah.
810-882-955. Oh, 8101, sorry. 8101 882-955.
Recording in progress.
Okay, cool.
Yeah.
All right.
Sure. Yeah, I was gonna. Oh yeah.
We want 2 years.
Okay. I was gonna say like once you're done talking, we can swap or something.
Yeah.
So whenever you want. Share your sweets.
All right, hey guys, our group is going to be presenting adversarial sensor attacks on ladder-based perception in autonomous driving.
Please also introduce yourself
Oh,
and say
sure.
which year you are.
I'm Krish. I'm a master's student doing computer science.
Yeah, I'm Double. I'm also a first year master's student studying computer science.
I'm Simon, first year master's student studying computer science.
All right, so let's move on to the problem statement. What's our problem statement? So a little bit of background. Autonomous vehicles or AVs use LiDAR and cameras for perception. They usually use this to see their surroundings, right? And previous work has been focused on looking at how we can make camera security more secure by, shining blinding light at it, shining lasers at it, making light go away from it. But the issue is that LiDAR itself hasn't been extensively researched in terms of its security issues. And so the goal of this paper was to study the security implications to prevent spoofing attacks. So some background, again, AVs use LiDAR sensors to see their surroundings. And what LiDAR does is it pretty much just sends out laser beams into the environment so that when the laser goes into that object over there and it gets reflected back, the system is able to measure what the distance and round trip time is to create this. So what attackers can do is they can actually send these LiDAR sensors or these LiDAR light rays into the LiDAR system and just kind of confuse the system into thinking that these reflected rays of light that are infrared light that are coming from the attacker are actually coming from an object in the environment, which pretty much makes it so that the system thinks that these lights are part of the environment, making them think that there might be obstacles that aren't actually there, which can cause crashes. So finally, how do we connect this to the lecture? So we see that LiDAR spoofing is an in-band transduction attack. And the reason this is the case is because transduction pretty much talks about how physical properties of the actual environment are changed in order to give some wrong information to this system that we're talking about. And it's in-band because we're using the same spectrum of light, which is infrared light, to kind of attack the system itself. The way that this attacker can do it is by having a range of being right next to the car and being able to kind of just shoot the lasers into the LiDAR sensor, or even by just being next to the car in a different car and just shooting the LiDAR sensors to each other. And the attack impact is that it kind of mitigates the integrity of the system, and it diminishes the confidence of the user that's sitting inside that vehicle for that actual system, saying that the AI isn't actually working correctly because it thinks that there's an obstacle there. And finally, we can kind of classify this as a physical actuation attack. We talked about physical, but actuation in the sense that when this physical attack is happening, the system is making a decision that actually actuates the car to either stop or to move or to do something like that. But what I want to ask you guys is, what modality do you guys think this is? Is this in modality? Is this like what type of modality? Same modality, different modality? Does anyone want to answer? All right, since we're running short for time, I'll just give you the answer. It is the same modality, which is IR lights, which is similar to TV remotes, but just a little bit more stronger and focused.
So we want to build the intuition of behind what exactly we see here. And so we see the obstacle spoofing can be successful in different scenarios here. The first scenario we'll talk about is what's the spoofed obstacle when the vehicle is stationary. And we can see that as there's this wall when the vehicle is at a standstill, maybe at a green light. And the second one is while it's moving, we see it can, if an obstacle is spoofed, it'll basically stop within a second of time.
So we can talk about the specific pipeline that the authors of the paper implemented. In the paper, it was rather kind of technical, so we just want to give a brief overview how it works and how it ties into everything we've learned in class so far. So first, starting in like the physical world, the adversary can send IR rays into the LiDAR sensor. Typically, as Krish explained, the LiDAR sensor sends out IR signals. It'll bounce off a wall or an object, come back, and then the sensor calculates the round trip time to basically create a 360-degree 3D map of the world. Instead, what an adversary can do, if they have the correct equipment, we'll call it like a LiDAR spoofer, for instance, this captures the IR signals that the LiDAR sensor is using to create a map of the world. It'll capture the frequency at which it's kind of sending those signals out. And then based on some delay, it'll return the signal to the sensor in order to basically spoof it and confuse it into telling it that, and to making it think that there's an object there when there really isn't. So after the physical world, once the data goes into the sensor, it goes through the pre-processing or like filtering stage. A naive approach to basically confusing a LiDAR system would be to get a really strong laser and then just shoot a bunch of like rays into it and hope that it somehow confuses the sensor and the entire pipeline. This is a naive approach that we could implement, anyone can implement if you have the right equipment, and the authors of the paper tried that as well. And obviously it didn't work, so that's why they had to create a more in-depth approach to it. There were two specific techniques that they used, first of which was in that pre-processing stage. They noticed that they needed to ensure that their fake spoof data made it through that pre-processing filter. So in order to do that, they conducted what's called an input perturbation analysis. And in layman terms, all that really means is they put in a lot of data into it, and then they observed what the output looked like. And then based on that, they understood how to manipulate the IR beams into passing through this filtering process and going into the digital pipeline, going through the ML model, and going through the post-processing stage. For the post-processing stage, the algorithm would still kind of remove some of the data. So they had to also implement a global sampling method to help optimize their solution. So that way the obstacles would still come out of the post-processing stage and give a wrong obstacle or a fake obstacle in the output.
So the way the authors did the evaluation here is they used the software called SimControl, which basically is a simulation that had collected real-world sensor data, and then it inputs into the simulation, so you can have like a virtual car that does exactly what it would do in real life. And the way we saw this is they added an attack trace, and we can see that a pristine 3D point cloud is created, but we see that there's actually spoof points created when the attack trace is created. And this is what it looks like using the naive solution. However, after doing a more thorough attack, we can see that there's actually a very high attack capability based on the number of spoof objects. The more spoof points there are, the higher success rate there was for the attack. And we can see that we can see here that the spoofed obstacle is created whenever there's a lot of spoof points done in the correct way. And we can see that this has been very successful. And even with further optimization by the authors, we see there's even more success there as well. And so some future works we have that we'd like to consider is that we thought that one thing they could do to kind of make this more thorough is do more real world testing for robustness against noise. There are definitely things like, sunlight, and other light, noise, things like that can affect the LiDAR in the real world, and we don't know how that might be impacted. Additionally, we want to generalize the methods to different systems. The authors had worked on a white box system here where they knew how the algorithm and system worked for this particular LiDAR. But if there was a black box system where they didn't know how the LiDAR algorithm or the whole system kind of works in general, we wouldn't know if it would work as well or not. So that's one thing we want to do in the future work. Additionally, we definitely want to improve the AV defenses. So we thought at the system, sensor, and ML levels. Kind of at the sensor level, at the system level, we want to think about things that using sensor fusion to ensure that if the LiDAR, something goes wrong with the LiDAR, we want to use radar, ultrasonic cameras, things like that to kind of make sure that if there's not really an obstacle, it won't notice that. At the same time, we want to look at, from the sensor level, we want to make sure we look at kind of some different mitigation techniques to make sure that even if there was some sort of spoofing action, we're able to mitigate it. And that can also be at the ML level where we might be able to train a model to detect adversarial kind of spoofing points and kind of know that's wrong and don't act on it.
Yeah, and since the release of this paper 5 to 6 years ago, there has been more work done in this field. We found a few papers about these. So first, we found a paper that actually conducted some adversarial attacks on black box systems where they weren't able to reverse engineer the specific modules of the pipeline and were able to expose a general vulnerability in LiDAR systems. Secondly, there was a paper that also introduced model agnostic defenses. So that essentially means there's a module component that you could apply to different LiDAR systems, and it should help defend against these types of attacks. And then finally, they also there is another paper that tested on fusion models, which combine LiDAR, camera, and radar sensors, and it actually found that using fusion models isn't necessarily the most effective defense technique, and that adversarial LiDAR attacks were actually still effective in producing fake obstacles. And then before we hop into our discussion questions, that was a little brief, so we could easily answer any Q&A questions before moving on. Cool, okay. We'll move on to discussion questions. If anyone else has any questions, feel free to ask at any time as you think of it. Our first question is, so this paper actually talked about adding a fake obstacle in front of a car to either stop it at a red light or in order to force it into like a car into stopping while at high speeds, risking like rear ending. But we thought it would be a much more effective way to, harm someone if we're able to remove an obstacle in front of a car and force a car into rear ending someone at high speeds. So this is something we were curious about while reading the paper, and we're just wondering if anyone had any ideas on how we could even go about implementing something like this, and more so how we could also defend against this sort of approach if someone was able to implement it. Yeah.
It's like one thing I was thinking of. You mentioned how like a lot of their like random like lasers are getting like pre-processed out. I wonder if you could try and do that to like an actual like real life object, try and like make it so noisy that it just gets removed and now you have a car that isn't there.
Yeah, that's a good point. Yeah. One of the things, one of the solutions also that like we were thinking about trying was also training like adversarial data in the ML model. So maybe using that information, you could also see how you could turn a car into adversarial noise and get it removed. Yeah.
Does anyone have any ways we could maybe defend against it? Maybe too much noise, like he said.
I mean, sorry, I'm going back to the last question.
Yeah,
you
sure,
asked, like, is there a way to like maybe like attack the receiver on the car to where like we won't recognize the waves coming back, so it won't see an object there?
Yeah, but so there's one caveat to that, in that if the LiDAR sensor is actually not even receiving anything in the first place, it's not going to rely on it, right? So I'm sure there's a way to kind of combine both of your ideas where you're adding so much noise that it kind of takes it away, but then also you're kind of not giving the points at all to make it seem like there's nothing there. I'm sure there's some way to combine both of those solutions. Any defenses anyone can think of?
Right.
Yeah.
But could the transmission be delayed so that if the object is perceived as being further away?
Yeah.
Yeah.
I think one thing that we were thinking of that could be a good defense is that to send like random lasers rather than having like a consistent way of just seeing whether an object's there, just sending the same amount of laser pulses at the same frequency, the same time, right? And yeah, getting reflected with that much noise, maybe the noise is only happening at a certain time duration or a certain sampling rate, right? But if you randomize that sampling rate or you randomize the amount of light going out and coming back to you, it could be a lot easier to make sure that this doesn't happen. So we'll move on to the second question. We already talked about a few defenses, like what I just said, randomization and also sensor fusion. What are some issues with using both of these or either of these? Does anyone have any insights?
Well, I know that like there were some attacks where like even if you have like a camera, like you just like paint a stop sign like a little bit differently and like it can fool like a machine learning model looking at the camera. So maybe like you could just combine both of those attacks to fool fusion sensor or sensor fusion.
Exactly. And then anyone have any insights on what kind of making the randomization, like attacking the randomization patterns? I can give a little bit of insight. Since the authors of this paper were actually working with the white box model where they're able to see the actual process of the LiDAR and they're able to kind of send those lasers out and put more data in, see the output. Anyone with a white box model would easily be able to tell what this randomization is, right? Because random isn't really random. There's some algorithm that does it. And so with white box systems, randomizations would honestly probably not even be, it'd be pretty trivial to solve. But with black box models, the randomization would probably be a pretty effective way to reduce these defenses. Yeah, and just real quick, can anyone think of anything else other than sensor fusion or randomization to kind of maybe mitigate some of these attack potentials or attack impacts that maybe we talked about or something that we just discussed?
Using humans.
Not having AVs at all.
Yeah.
Yeah, does anyone have any like final questions or concerns or maybe some interesting topics you guys want to discuss? Yeah.
Have we seen randomization be done in the wild? Like I would imagine that's like really compute heavy to figure out your 3D map.
I think that the authors did suggest that that was something that they wanted to consider. So we actually, I assume that has to be something other researchers did in future papers since this was released, but that is one of the few defenses we didn't double check to see if someone tried it and saw the results as to how that worked.
Yeah. The other like randomization, not just like with the interval times, but also like the wavelengths of the infrared and things like that. So there's definitely multiple avenues you could go with randomization as well.
Yeah.
What are those for?
If any of you guys have played Fortnite, so these are pretty much what you kind of use to give yourself extra health and extra defense. It's a healing pack, pretty much, yeah. And if you go back to the last slide, or the last two slides, I don't know if you guys have played Kirby, but sensor fusion with all of our LiDAR, camera, radar, a few little Easter eggs here and there. Yeah.
All right, let's thank the speakers. Very good job. I like the interaction. It's very good.
Thank you.
Can we have the next group?
Yeah, Alex, do you want to present?
Yeah. Yeah, so I mean, sensors, either specifically, it's been one of those things that there has been lots of worrying about the fact that people can shoot lasers and all, and fool them. So this was very interesting. All right, so second one is about deepfakes. All right, guys. Take it
Hi.
away.
Hi, I'm Leon. I'm a third year computer science undergraduate student.
Hello, I'm Alec. I'm also a third year CS major, undergrad.
Yeah, I'm Anthony. I'm also a third year CS undergrad.
I am Andrew. I'm a third year CSE undergrad.
And so we're going to be presenting on detecting audio deepfakes through vocal construction. sorry, vocal tract reconstruction. And
Oops.
oh, sorry. Okay, so the problem is recently there's been a huge rise in like using machine learning and AI methods to generate basically fake people. So as you can see from this cool illustration of Obama being deep faked, you know, they're getting pretty good. They're like a lot of humans have trouble detecting like, is this a deep fake video or audio? So this paper kind of goes over how do we defend against specifically deep faking audio. So I guess a little bit about the type of attack. Like we said in class, this is a bit of an impersonation attack. So like we're like mimicking, you know, someone. And you can think of this as maybe it doesn't quite fit in with the CIA model too well, but it's kind of fitting in with like the integrity, the integrity of, you know, videos. Like videos are used as like court evidence. You know, we're attacking the integrity of that. And this defense specifically is extremely strong because it can like it has very few assumptions. It like uses a black box model of these machine learning algorithms of generating new voices. So it's a very strong security model. Okay, so a little bit more background about like GANs, which is kind of the method that they used. So when we're doing like these vocal tract or when they're like generating vocal audio, they usually use GANs. And the problem with GANs is that they kind of learn the data's distribution, so they can't like learn very specifically about one person, which is kind of the problem that that this paper exploits with the vocal tract reconstruction.
All right, so getting into the methodology. So just a little bit of background almost is what they're going to do is try and model what is known as the vocal tract, which is how we like make sounds. So down here at the bottom, we start with like the vocal cords, which vibrate when air goes through them. And then we have this entire vocal tract, which changes shape in order to make different sounds and let us talk. And what happens is if you just look at this graph, this is like a graph of the cross-sectional area of the vocal tract given two different sounds. So here on the left, we have like when you say who, you can try saying that to yourself versus has, right? You can feel your vocal tract like making different shapes. So what they did is we need to make a mathematical model. So they went ahead and modeled it as a pipe with different diameters. In the end, they ended up with going with around 15 different equal length sections of pipe, all connected with different diameters. And then what they did is they said, okay, so we have our model. How do we go from an audio sample to figure out like what this pipe, like all the diameters of each section of pipe is? Well, they essentially look at the frequency distribution and then use a process that's kind of like optimization whenever you do any kind of AI training, but more grounded in like actual physical phenomena, and essentially take the frequencies and kind of like use some optimization to reverse what that model, like the diameters of each section of their model is, to come up with the various cross sections in the vocal tract for any given audio sample. What audio samples are they using? Well, they look at what they call bigrams, which you can think of as just different sounds you make, but specifically a pair of them. So if we say like go Bruins, we say a lot of different sounds in there. If you put it into IPA, this is what it looks like. And they essentially split it up into different sounds. So each one of these is a bigram. And in the future, they will look at each bigram individually. And what they noticed is for each bigram, if they take regular audio and then they take deepfake audio, put it through like their vocal tract estimator, they notice that the cross-sectional area for certain bigrams might look like this, where there's not much difference between a deepfake and a regular audio. But for some bigrams, they noticed that deepfake audio is wildly off from what people actually use when making that particular bigram sound. And this is the basis of determining whether audio is deepfaked or real. Yeah.
There. So let's take a look at what the researchers actually were able to conclude. For their testing set, what they did, for their testing set, what they did is they took about 1,000 audio files from about 51 different speakers, and they from that extracted about 12,000 like bigrams to try to differentiate deepfakes. Here's kind of a graph they made of like some of the most common bigrams in like between like real audio and fake audio, and you can see how this is like kind of significantly different they are. There's like a pretty significant difference here. And so what the researchers actually were able to do is they actually managed to build a model that using those 12,000 biograms achieves a 99.9% precision rate and a 99.5 recall rate on differentiating between real samples and deepfake samples. And again, like just to emphasize, what's really cool about this is that they did this with a really, really small training set. They did like, sorry, the really small training set, I said 10 set, sorry. A really small training set of 1,000 samples compared, and especially when you compare this to say using deep neural networks, which require like huge amounts of input, this is like really interesting. Additionally, again, like consider the security model. They need to be able to determine whether or not something's a deepfake from a possibly unknown attacker. And so being able to do this using a very small number of samples is very, very helpful towards that security model. That's kind of a graph. This is like when they ran this on the evaluation set, this is actually what it looked like. And you can see like again, like the organic samples and the deepfake samples are just completely different for the most part. Yeah. Oh, there we go. Another thing they noticed is that like now that they've tried this attack on like some publicly available models, the researchers actually went to a couple of startups and asked, "Hey, can we try this against your proprietary model?" And most of the startups actually said no. There's this one called Liber though that provided them deepfake versions of presidents saying things. And so what they did is, like they compared that against like State of the Union addresses, and what they found is unfortunately their model is not quite transferable. But if you retrain like their model on like President Obama and President Trump samples, you can still the same idea still works. It's just that you have to retrain it on somebody close to like the target person. So yeah. Here's kind of a it's not the right graph. Here's kind of a it's fun, yeah. Also as kind of an example, if you just try to say the word dough, this is a really, really odd bigram, like dough. But like, if you try to say that, like, this is what your vocal track should look like. What the researchers found is that for basically all the speakers they tried, this is what the vocal track actually like. This is what the deepfake vocal track looks like. And notice that it has no structure here. It's like a drinking straw. It's like completely inadequately incorrect, which is kind of cool. The researchers also tried to basically compare their thing against to a deep neural network. And what they found is that deep neural networks do not generalize this problem very well. Using like their physically based model was a lot more powerful than a DNN, and that DNNs just have terrible loss when trying to do this model.
Okay, and then for applications of this, obviously, yeah, for applications, this in class we talked about the dolphin attack, or trying to attack your like AI assistants, and this would obviously be very useful with 99.5% recall. Additionally, we have like for biometrics, any like voice print checks. If you're trying to check, this would like be very useful for combating that. And as well as like defense in depth, in addition to like other like previously developed techniques for detecting deepfakes, you can add another like very accurate model on top of that. And obviously, like one of the things we noticed was that like, in the recent election, like deepfaked like, robocalls or scam calls, or that you can't really tell that they're fake. And this would be nice for like anti-phishing or anti-robocalling detection. And then for future work against this technique, as Andrew previously stated, they did attempt to contact many of like the commercial startups with closed source models, but most of them said, no, we're not going to provide anything, or like provide like 2 or 3 samples. And so redoing this technique against more current deepfake techniques and proprietary algorithms, like for example, like 11 Labs, how would you counter this technique with using like, could the AIs like actually learn to create those like realistic vocal tract structures? And even if it's computationally inefficient, can we just throw enough GPU compute at it to break through anyway? And then finally, we have our further discussion questions. How could this technique be implemented like, in real life in all your devices? Obviously, a 99.9% precision would be pretty useful. This work was done in English for like a normal speaker, and as Andrew said, it's hard to transfer. So how do we apply this to other languages, different accents, or those that have speaking disabilities? And then finally, are there ways to use these similar techniques in images or videos? People always complain about like uncanny valley, this just doesn't look real. Well, is there like a physics-based explanation for this? And can we detect that this AI is just not like following the laws of physics? And for that,
Let's start with the first question. Does anyone want to answer that? Any thoughts for like ideas or devices or anything you've seen in your real life where it might be helpful to know if somebody's trying to deepfake it? Yeah, go ahead.
Maybe for like a voice assist, like for an assistant or commands, it could only respond to your voice. And then after checking, make sure it's your voice, it could also check to see the deepfake as well.
Yeah, very good. Yeah, I mean, technologies nowadays, like Siri, I know tries to, for example, only respond when it's you saying it, right? But maybe a deepfake could get around that and start applying maybe a dolphin tag on top of whatever deepfake audio you're generating. So maybe this kind of technique could stop that kind of attack vector.
And I will say, I'll add to this that for the paper authors, their work is actually partially sponsored by the US Naval Department. And the reason for this is, you can think about this, on a battleship, if you're receiving commands from a commander, you probably want to know if that command is deepfaked or not. So that's a very real world use case they were thinking about. Now for the second question though, what do you guys think? Like, how do you think you could like generalize this to like other perhaps not as Englishy people? I don't know.
I figure you could probably do some sort of like mixture of experts model where different languages, just because different languages speak so differently, putting it all into one model is probably going to just make it worse on all languages. So if you just train one in like Japanese and one in Chinese, and you cover each language, and then you have another model that first identifies the language, and then you can do deepfake detection based on that. I think that would probably work better, although the model size would probably be kind of insane.
I mean, comparatively speaking, this model is not that large compared to like other AI models. So it also depends where you're trying to put it. If you're trying to put it on your IoT device, you might not want to make it that large, which actually makes this really nice.
I mean, I
What
guess
if someone is communicating with multiple languages, like in like, like switching from one language to another like mid conversation, or using different like words from different languages like in a sentence? Then it would be definitely, it might be there will certainly be like more overhead going into that, trying to detect whether this is a deepfake or not.
Yeah, maybe like a solution to that would be like you have one model, like a standard machine learning model that classifies what language is being spoken at each word, but it would still mess with like how the words are kind of like they were talking about like diphthongs, which it's like merging between two syllables. I don't know if it would be able to like still handle that with like constant switching. So it's kind of an interesting question.
One thing I didn't mention here is that, right, when they were actually training the data, they needed to divide the audio up into these bigrams. So they actually used other models. I think they tried like Google's Cloud, but it just wasn't accurate enough in terms of like the exact millisecond timestamp. So yes, there wasn't another model used to essentially label the data before they put it into this model. So that's another thing to think about.
yeah, then I guess we can go into the third question of, can we do this for images or videos? Like, is something like physically wrong with a deepfake?
I think that we just submitted a proposal on the last point.
Do you want to answer the question?
We are doing research on exactly the stuff.
wait a minute.
Well, there's your future work.
But yeah, so to kind of like to give you like what we are trying to do is like things like depth, for example, in real images is very different than deep pictures. So you can actually measure that to figure it out.
Does that also work on videos, or are you specifically looking at images?
Well, you do it frame by frame. Another thing actually that for video works is motion. So the idea is that the motion, like if the camera is you are using the camera, you're moving and you're shooting a video, deepfakes cannot properly model the motion, but real videos can. So you can actually find the discrepancy of the motion.
Yeah, there's somebody in the audience.
I imagine like maybe like ray tracing or something. Like I imagine like these deepfake videos tend to like exactly like model like how light is reflecting off multiple different types of surfaces. So yeah, probably, and that's like kind of like mathematically computationally expensive, right? Like video games and such. So I imagine like, there's something to analyze.
Yeah.
That
But these are dangerous because these machine learning models are like getting better every day. So you cannot really rely on the fact that things are not doable now, because in 2 years it might be doable.
Well, also some of the models do have compute like lighting, like Nerf models like implicitly learn like ray tracing. So I don't know, maybe eventually they'll like add that into like diffusion video.
That would be something would be also interesting.
Actually, something I wanted to point out is that like when I was in high school robotics, like one shot depth perception was like a huge research field. So like I'm thinking like, wait, it's coming back now, but now we can use it on deepfakes instead.
Yeah. Well, deepfakes is like exploding. So any research, especially like US Army, US government, very interested in deepfakes. So it's actually very hot area of research. Detecting, not generating. All right, thank you guys. Great presentation. Do you want a break or should we continue? I think we can do one more. Let's do one more. Who's the third group? Are you guys the third group? Well, lots of great ideas about deepfakes, like that everybody has. But for projects, also deepfakes detection could be a good option because it's very easy to generate deepfakes. So you may want to consider that. Also, I like this paper because like for many of its good lessons, it's like you always think that, oh, okay, let's throw machine learning at things and it will work. But as you can see in this paper, they're actually trying to use physics and using some form of rules first. So just keep that in mind that not all the time machine learning is the right choice for many of the solutions. It's the numbers is there. Yeah, go ahead.
Okay, hello everyone. My name is Yiwei Chang. I'm a first-year master student at EC department.
And I'm Yi. I'm also a first-year master student at EC.
My name is Hayden. I'm also a first-year master student in the EC department.
And my name is William, and I'm a first-year PhD student in the EC department.
So today we're introducing light commands where researchers have used laser injection to attack voice controllable systems. As we have discussed in the lecture, okay, it's not working. Okay. So as we have discussed in the lectures, there are tons of vulnerability when it comes to voice controllable systems. One of the major issues is that they often prioritize capabilities rather than security. So it has led to some of the previous known attacks, including the ones that we have discussed last week, dolphin attacks, and also we can use synthetic audio to inject malicious command. But in this paper, the researchers, they focus on laser injections. We would assume that the microphone captures acoustic signal only, but it also captures light signals, and that's kind of the problem. So before we get into that, let's take a look at MEMS microphones. This microphone is widely used in it's mostly used in the voice controllable systems. It has a diaphragm that flexes acoustic sound and then convert them into voltages signals. But however, they are also sensitive to light. So in particular, the photoelectric effect can tamper with the circuitry, and the photoacoustic effect can convert light signal into kinetic energy and potentially vibrates the diaphragm. And we'll take a look at that in just a second.
Okay, so now that we covered the vulnerability of MEMS microphones to lasers, there's motivation to find a technique to embed a signal of interest in visible light. And this is done through something called laser signal injection. So similar to other parts of the electromagnetic spectrum, such as radio, it's possible to encode a signal in visible light by using modulation techniques. So in this case, it's sort of an analog to amplitude modulation where your message is embedded in the fluctuating brightness of a laser. So most lasers consist of LEDs, and the intensity of the light emitted from an LED is roughly proportional to the current flowing through it. So if you have an audio message, you can modulate the current through a laser with accordance to the acoustic characteristics of the audio signal. So loud sounds would result in greater variations of the current through the laser and therefore the brightness, while quieter sounds would result in less variation. So using this technique, you can successfully transfer an audio message into an optical medium. And this leads us to the basic attack model. So this is a signal path of the attack model used in the paper. So the first part you would have would be some sort of a signal source. So this could be like a laptop or a sound card. It's connected with an audio amplifier into a current driver. Current driver is sort of like a specialized piece of lab equipment, which you use to tune and fluctuate the current through an optical device. This would be then connected to a laser and directed at the MEMS microphone ports of the target audio device. So as discussed before, the microphone will pick up the laser stimulus as if it were an audio signal, and an attacker would be able to complete an attack on the device and elicit an audio response by only using light. The evaluation method used by the paper was that an attack was considered successful on a specific device for a power budget and range if a command was able to elicit a appropriate response 3 times in a row successfully. And for various devices, this is organized here in the table. And the main takeaway is that pretty much every single popular household device and personal device, such as a smartphone, is vulnerable to this attack with a laser that is at least 60 milliwatts. And even though in the US, most lasers are confined to be within a power budget of 5 milliwatts, it's pretty easy to find ones that are powerful as 600 milliwatts on websites such as Amazon. And even weaker lasers, you can still exploit certain devices up to extensive ranges, which means that this attack is actually pretty feasible and affordable to carry out for most people.
So there are several potential attack vectors. The first one is a low power cross building attacks. As we talked before about the long range attack, we just assume the microphone ports be on the side of the target device. But let's see in a more realistic scenario that the attacker is in a faraway tower, which is higher than the office building, and it uses some telescope to aiming and focusing on the target device, and also the target device is a Google Home device with its microphone port on the top of it. And as a result, and the distance between the target device and the attacker is very far, like 75 meters. And as we can see from the result, even with a very low power consumption, like 5 milliwatts or something, the attacker can still successfully inject the voice command into the target device, even penetrate through the double pane glass window. Yeah. And the second attack vector is the ping attacks, because many applications now use some digital pings. And as we can see that the digital ping, the spoken ping is kind of vulnerable, because the ping eavesdropping is feasible by simply remotely using the laser microphone to sense its acoustic vibration. And there's also ping brute forcing. This is because many big companies like Google just delegate its ping verification to some third party device companies, which sometimes implemented incorrect ping verification mechanisms. And to be specific, we conducted attacks on August Smart Lock Pro for most of the Google Home device. And we found that there's no limit on number of attempts of the ping codes, and also no implementations on time delay mechanism between incorrect trials. So that is to say, through simple enumeration, we can just break into the system by trying all the possible codes. And also, there's a ping bypassing. That is, some commands do not require any authentication. So even if some commands are not available at the moment, we can use some alternative commands to achieve a similar goal. And the third is car attack. This is because for most of the modern car companies, it allows the users to do some operations remotely on mobile devices, which is often combined with a VC system, like Tesla and Ford. And for Tesla, that one is EV car integration, which provides information of current location, locking and unlocking in the sector, and it implemented voice control even without a ping. And also that is Ford. For Ford, that is Ford Pass. It requires ping for engine start and door unlocking, but as we said before, we can use just ping brute forcing to just break into the system. And also it's worth mentioning that you still need extra actions to shift out of the park status.
Yeah, so going into that, there's obviously quite a few countermeasures that you might be able to think of, especially given it's a laser. So the first of which is, given it's a laser, you need direct line of sight. This is obviously key to this. We do note that like you might think of maybe diffusion layers or like fabrics. That's not exactly going to block it, but at like a wall, for instance, you definitely need to be able to see the object. Second of which is sensor fusion. It comes in ways that we think of and ways that we don't. So the one you might think of is obviously just like detecting the light, right? Seeing if someone's doing this. But also, if you think about it, light is only pointed at one sensor at a time. It doesn't have a range similar to what your voice might have. Like I'm projecting outwards, I can hit multiple microphones at once, while your light beam will only hit one. So in that way, multiple microphones can actually be a cost-effective solution to both capture more audio as well as to capture this attack. Next of which is what they call liveness checking, which is when basically your system asks you to confirm who you are. It's like when it talks to you, but this system can't hear. And obviously, since it can't hear, you can't understand, you can't really read out a CAPTCHA, you can't do anything like that. Last of which is diffraction barriers. This is just simply putting a light diffusion gel around or a diffraction gel around the MEM microphone, and that could be a feasible barrier solution in hardware alone. With that, there's a lot of future works that we identified both from the paper and from not. The first of which is other sensors. So this comes in multiple facets. Just gonna give you 5 seconds to think what else lasers can do. So with that, I'm not going to ask what for the sake of time, but lasers also generate heat, and heat can seriously generate kinetic energy as well, which can be used to attack IMUs. This same concept can be used to hit IMUs, gyros, anything of that sort. The next thing is obviously heat. Both those kind of go hand in hand together. And the last is reading information. Theoretically, depending on your speaker and the system the speaker does, you could also extract information from laser from light sources itself, and then you get around that liveness checking. So with that, we got a couple of discussion questions. The first of which is, how else can you envision lasers being used to transmit information? That's an open question to the audience. And obviously, I opened it up a little bit. It could be used to transmit through heat, different signal sources, but also this kind of goes hand in hand into how can lasers be used to capture information as well.
Yeah. Go ahead. Well, I have a question, which is like, how does the laser like make the speaker, like
yeah. So the description of it is basically the photoelectric effect. So without getting like too deep into the physics of it, effectively what happens when you shine the light into the MEM microphone is it actually generates a capacitive signal into the microphone, which is similar to what happens when the diaphragm moves as well. So then in that generates the same signal into the computer or whatever's capturing it. Any other questions?
I guess the one thing, since you were talking about like, what if we have like a capture system where the resulting laser can't hear? But I do think that there's been research on like seeing like, well, like hearing, like especially like EN speaker things through walls. So I wonder if you combine like this research with that research to then defeat like a capture system and therefore like transmit information anyways.
No, that's a super great. There's someone in Northwestern. His name is Karan Ahuja. So his work is in similar exactly what you described. So he uses RF signals to go through walls and then track where things are. So as you said, it could be used to capture information, but it can also be used to aim your system. It can be used to find where that microphone is, find where the home is, target it. Definitely, there's other signals can be used in tandem, not necessarily even to capture data, but just to position in the first place. And then a couple other things. I have one I think is fun as how can we implement non-intrusive voice authentication? So in this paper, we talk a lot about design questions where it's like, how much trade-off do you get between convenience of this product? Voice controllable products are like the pinnacle of convenience for most people and security, right? Where these live pins that we're using, honestly speaking, most people hate them. Most people hate using them. I'm sure you guys already hate using Duo. So it's kind of a discussion of insecurity and design and consumer product. How do we find that balance between what is easy to use and how can you envision? Some of the examples I can give potentially are nod authentication. That's a thing in VR headsets for the same idea, where your nod has a fingerprint for yourself. That's also a discussion. And then if anybody has any ideas on that.
Yeah, another presenter talked about like audio deepfakes, and in this sort of same sense, we can have some kind of machine learning model that can detect like particular voice authentication that way.
Yeah, that's like great. So basically, that's one of the things in these like kind of voice control systems, they try to train off your voice. But what they actually found is that in the next question is like, theoretically, you could also synthetic data to recreate their voice too. So it's kind of a cat and mouse cage, which is like most security, where you can attack in the same vector as you can defend. So synthetic data approaches can both be used to, to keep your system safe. But at the same time, that voice signal is one-to-one in the laser, which can also be used to attack that same product again too. So definitely like very interesting because we can have fingerprints in the voice, we can have fingerprints in training, we can keep the voice safe. But at the same time, like we could also put that in the laser too.
I guess going back to your first question, something I've been thinking about is like, maybe you could do something with hard drives, like the recent HAMR technology. They use like lasers to expand like little sections of the magnetic film. So maybe you could like use a laser to make it read the wrong location in the disk by hitting a part of the hard drive, although I don't know how you transmit it into a hard drive.
No, that's really interesting. Like for sure, we could even corrupt systems, like not even the data that we get, but the system itself, like in hard drive sphere and like magnetic spheres, anything of that sort.
Cool. I mean, for the interest of time, we can definitely have more discussion offline, but thank you, Ms. Stankin. Let's have a quick like.
Presentations you've melted.
Like, kind of a presentations folder. So let's continue. So with underwater now, we're exploring different modalities. Go ahead, guys.
All right, hello, I'm William. I'm a first year master's computer science student.
My name's Nabil. I'm also a first year master's ECE student.
Hi, I'm Jackie. I'm a fourth year undergrad.
I'm Audie. I'm a master's student in ECE.
All right, and this is Aquasonic. All right, so essentially this paper goes over underwater data centers and their vulnerabilities, specifically to acoustic injections. And this is essentially when you place a speaker in the water, it plays some sounds and it messes up the hard drives inside of the data center. And also this paper focuses less on denial of service, but more on targeting specific parts of the data center so that it can like redirect the workloads in the server, change the resource allocation, and control like latency and throughput. So what this paper goes over is that these attacks are actually really effective, but there are still some defenses to this. A little bit about the background of underwater data centers. They're just data centers that basically like cloud. If you use Google Drive, it's probably hosted in like cloud server, which is in a data center. These are the same things, but underwater. And these use hard drives, unlike your computers that probably use solid state drives. And this the reason for this for all data centers is because they're cheaper, they last way longer, and they're just better for the case. But the hard drives, the main thing about them is that they have moving parts. And specifically, they spin and they have like some resonant frequency, which can be targeted. Underwater data centers are also surrounded by water. They have some benefits to that, like the cooling, the space efficiency compared to land. But because they're underwater, it's much more dense and sounds are able to propagate through water much more powerfully.
So these acoustic injection attacks are similar to some of the physical attacks that we've looked at in class. But the main idea is that the adversary will send this acoustic signal or sound waves through the medium, which in our case is water. And at the victim UDC, it'll induce some mechanical vibrations, and that translates to potential like disruption of service or denial of service. For example, the throughput of the UDC can be degraded, or there can be increased latencies. And generally, the attacker will have some knowledge about this environment and physical properties of the victim, which they can use to design their acoustic signal. So for these attacks, the main thing that we really need to model and look at is really the magnitude of the induced vibrations. And that's especially important in hard drives because they have this mechanical actuator arm, which is responsible for the read and write operations of the hard drive. So if you have vibrations coming in and disturbing that arm, then you'll have a drop in your read and write capabilities, your rate, and eventually throughput. You can also see in this graph that, as you'd expect, the amplitude of the adversarial signal has a positive relationship with how much that arm is displaced. So the attacker will design their signals so that as it propagates through the water and attenuates over whatever distance that they're attacking from, it'll still have a certain amplitude at the victim. Attackers also have an advantage underwater in that the sound waves travel faster than in air. So that gives them a little bit extra power transfer for them to utilize in this attack. Also very important are the resonant frequencies of the material that the UDC is made of. If the attacker can characterize those frequencies and design their wave around it, then they can really maximize the amount of power that's transferred from their signal to the vibration and displacements. Other things they can do are, for example, they can change the location and the direction of their speaker to target more like vulnerable parts of the hardware. So you can see there's like a lot of physical variables that the attacker has, at their disposal to change. So that if you try to like reduce the impact from one, they can adjust in other directions and account for that. Also, like William said, there's some more advanced attacks that attackers can do. If they have some knowledge of the system architecture or how it's distributed, like for example, if you have a distributed system with multiple nodes, they can attack certain nodes and then displace, or they can attack certain nodes and redirect that traffic to other nodes, which can overload your system and increase the latency of the overall system, not just like that node that they targeted. So that's really what this paper is looking at, trying to look at that context and offer solutions for it.
So in terms of the proposed solution and contributions, the paper basically characterized like how certain factors like the speaker location, orientation, sound, volume, and frequencies can be like used to manipulate things like software and hardware. And on the right here, you can see they look frequency sweep, where every 5 seconds they increase the frequency by 100 hertz. And you can see like when the throughput gets low, that's like where you can think of like the resonance frequencies happening. And then in terms of like the paper's proposed solution, they basically created an ML model, which is like k-means clustering, to basically detect from these throughput numbers. Like they basically trained it on like with no sound, like the throughput, and then with sound, the throughput, and then did like a k-means clustering. And with this, they basically got like a 98.2% true positive rate and a 0% false positive. And then it also suggested defenses like passive attenuation with absorptive material. And you can see on the right over there, a consideration they were talking about was how it increased temperature. So you can see with absorptive material, it's way higher. So it's like a trade-off they were discussing in the paper. And they also talked about active noise cancellation, which is, just canceling noise, but it has like environmental impacts. And they also talked about post-detection like defenses, because their solution is a detection model. So they're talking about having a replication. So if a server is being attacked, you have to like redirect that traffic to somewhere else where your data is replicated. And then for the evaluation methodology, they use RAID 5, which is like fault tolerant hard drive configuration that is used in many data centers, hybrid SSD architectures, basically in the lab and open water scenarios that you can see on the right over there. And then basically they utilize the speaker to deliver this attack from various locations and orientations. And Yeah, they also characterize this impact on well-known softwares that are used in data sectors like CockroachDB, OpenNebula, and Hadoop, which are all have some distributed component to them.
All right, so now that the boys went over a deep dive of the technical aspect of the paper, I'm going to talk about kind of the main results and what kind of insight that provides to us. So I summarized a couple points that were specified in the paper, but what exactly does this entail? So first, acoustic injection attacks can be quickly harmful and almost immediately degrade performance of the individual components and then eventually the entire underwater data center. And second of all, because it is underwater, there are a couple different complexities with the different types of attacks. So number one are the long range attacks. So your kind of adversary doesn't have to be really close to the underwater data center to attack. It can actually make attacks for like up to like many kilometers away, which poses a unique challenge to the underwater detection and defense. But also because it's underwater, you can't exactly control the natural environment around you, which means that people who do more subtle attacks, those subtle attacks can actually go undetected because you'll just consider them as like normal operational anomalies. And then, you know, that obviously will lead to a bigger detriment when those subtle attacks keep happening and then affect the overall system in the long run. And then for some potential work, the first is hardware and material innovation. We want to be able to explore advanced soundproofing materials that are optimized for underwater environments. So that means not only us as like ECE engineers or CS engineers have to focus on this kind of innovation, but also maybe working with other interdisciplinary groups like material engineering to figure out how we can optimize the systems. And next, there is a trade-off since our underwater systems are in underwater natural environments. We want to investigate defense mechanisms that don't introduce noise pollution or negatively affect the environment that the underwater data centers are in. AKA, if we have a really good defense mechanism, but then it ends up killing like all of the fish within like a certain range of the underwater data center, that would not be very good. And lastly, we want to explore the idea of scaling open water defenses. So maybe doing some research about like using military grade technology to see how far or how effective like long range defenses are, and then maybe deploy some underwater surveillance systems to detect these long range attacks in the future. So that is that. And then we have discussion points, but we'll open up for questions before discussion points. Jake.
Yeah, I don't think I caught it. What is like the frequency range that these attacks use? Is it super high frequency or is it pretty low frequency?
So here they're looking at 10 squared to 10 to the 4th. So the range that the paper was
I
testing.
think it's acoustic, so it has to be within the range of acoustic, so hundreds of, like tens of kilohertz.
Any other questions?
Yeah, like the frequency they're looking at are like, you can see these sharp drops in the throughput. So the paper was really looking at the frequencies that are associated with the resonant frequencies of the material. So that's what they're characterizing with.
But I'm not really familiar with like underwater data centers. Like, how is it usually like physically work? Is it like some big casing and there's like water on the outside and water on the inside? So is that thing also filled with water?
Or if you go on to the next slide, yeah, the test rig they use, they have water inside.
Is it always water, or is it gonna be like, is it just straight up water? Or is it like maybe some other liquids sometimes, like different like viscosity that would like affect the resonance frequency?
I believe it's just water.
It's just
Or,
water.
yeah.
Well, to make it cheap.
It's like how does the computer not die?
Yeah, they have like separated, okay, before I read this paper, I also had like the same understanding of like, what if you just poke a hole and flood water in it? But no, there's like separate components are like that are more water sensitive are sealed off, and then
So it's
other things.
tubes, right? So it's like there are like liquid, like I don't know if you've seen, like if you have a roommate that's gamer, they have like, have you seen those liquid
Like circulate water in and out. of
Yeah.
this thing? Oh, okay.
I don't think they even need to circulate, so this thing is kind of floating, so I think the water is basically just floating by itself.
But it like passes through some kind of radiator inside. Or is it just like
It's ocean, so like the thermal coefficient is almost infinite, so you don't need to do it.
do they like purify the water before it goes in, or like how do they prevent it from like building up gunk everywhere?
So I think it's a heat exchanger, like you're not actually running seawater through the it's just a heat exchanger and you're exchanging the heat from the cooling to the.
Yeah, probably some cooling going in and then the cooling itself and then it's connected to. But I'm pretty sure that this is mainly Microsoft, so Microsoft has some videos. I've seen videos that they kind of put the thing inside the ocean. What's that?
I don't think they canceled a bunch of the underwater data, like recently.
I
They said it was like not profitable.
Okay, so going into our discussion points, the first
We
one.
just talk about one of them.
Yeah. Let's just talk about the first one. How do acoustic injection attacks challenge traditional notions of security and trustworthy competing systems? And what new threat model should be considered? Any ideas? So I guess like what kind of, the way I would think about this question is kind of like, it's very different from anything that we've studied. And how would we have to approach kind of defending these sort of systems from such attacks?
I guess traditionally it's more like you worry about like the electronic security of your servers, right? And you're like worried about someone's gonna hack into them. But I guess here it's more like you have to worry about the environment, your servers, and also, which normally in a normal data center, I guess it's not really a concern because you kind of have your own secure data center. But I guess when you're kind of throwing your computers in the ocean, it's not really like, I guess your environment is very secure, which also like the question if like someone could like go steal them physically. Like I guess like the difference between them doing that or just doing the like why not just like attack the thing instead of like using sound? But yeah.
Well, this is what we call in the wild, right? Like so there is like difference between things that you have at home or data center versus things that you just distribute in the wild. Like utility system is also the same, right? Like you have a big utility distribution center somewhere in the middle of nowhere. And you cannot physically guard them, right? So there is like next level security that you need to implement.
Yeah, I'd also imagine underwater data centers specifically, like there has to be some sensor that's measuring the pressure, otherwise like your thing might get crushed. So like I guess you have to also think about the security of like these sensors and like other types of objects that are like guarding your data center. Cause like I'd imagine like acoustic injection could maybe like, I don't know, modify the pressure some way, maybe it's less or more pressure and then like cause certain issues there that people are not taking track of.
Yeah, I would say like, I don't know, heat, like, the system is heated up or, yeah.
I'd also imagine, I guess you guys were talking about like, I'm not sure if I followed it correctly, but you're talking about like the hard drive, like these data centers using hard drives and like maybe like the read pin or whatever, or the read, what do you call it? The read like head, read head like moves with this acoustic injection. I guess like normally we have like databases and databases have like transactions. So if it fails, like you get it again. But like I guess like if someone had like a white model of like your system and knows when the writes are happening, they could like theoretically kind of like make your writes go to a different place than you expect, and like that could.
So this is RAID 4, so that's why they have redundancy.
Right.
So even if you manage to kind of pull up one, usually the others pick it up. But that's why usually the throughput is really the one that hurts because of these redundancies.
Yeah.
Maybe last question from him, and then we can move on, but then the rest we can do offline.
Yeah, so I was like wondering maybe like could these like attacks also be used for like other underwater technologies like such as like the underwater like cables that communicate information. I don't know if you know what I'm referring to, the fiber optic cables like that run throughout the oceans. Like could this attack also be like used in that kind of application, do you think? Or would like other attacks be more would other attacks be more effective for those underwater cables?
I think these attacks would also be effective towards those, which makes it the challenge of like deploying surveillance systems or other, it's really challenging because like anything that you would deploy can also be subject to this. So that's the complexity of the issue.
I think
One mind,
yeah, I think these systems are also a little bit more, sensitive than your like fiber optic cable maybe. So maybe you need more like higher volume attack or more specific
Exactly,
attack.
versus the optics of frequency range might be way higher. So acoustic probably won't work, but something else. All right, thank you. Thank you guys. Great presentation, last group. Since the discussions are lively, I'm gonna let it continue, although we're a little bit over time, but I think it's helpful for everybody.
So I.
Alright.
Can you, is that, do you know how to, I don't know how to project, yeah. Is it? Let's just make do like this, then it's fine. We'll make do. Here. I guess this works.
Hi, I'm Michael Suji. I'm a second-year master CS student.
Yeah, I'm Edward. I'm a first-year master student, and we're presenting on this volt schemer paper, and it talks about how we can use voltage noise from a power adapter to manipulate wireless chargers. Right, so let's talk about what the problem is. So certainly some part of the problem is this notion that wireless chargers are safe. And in fact, this is not an assumption that we can make. The idea is that, you know, with traditional charging systems, you have this cable that can transfer data and that can be leveraged to, you know, perform some kind of attack. And people think that, okay, wireless chargers would communicate through some kind of, I don't know, basically magic in the air. And there's no data transfer, so supposedly they're safe. Well, in fact, this is not true. And it's because we have these sorts of two channels of information. First, we have this kind of analog channel through from the power adapter to the charger. And we can leverage this through using some kind of voltage noise, and we'll talk a little bit more about what that is. And second, when we get to the charger, we use this protocol called the Qi wireless protocol to send information between the charger and the device. And this is kind of more in the digital domain. And in fact, it's because of these Qi packets that are sent that, you know, makes a lot of these attacks quite potent. And finally, if we sort of combine these two domains, we realize that we can take some kind of finely tuned voltage noise from the power adapter and perform some operations on it and deliver some kind of malicious Qi packets. So let's talk a little bit about what the threat model is. So we assume that, okay, the attacker needs to have access to the power adapter. Without it, they're not going to be able to send this voltage noise. Okay, and the second assumption is that, okay, if they have access to the power adapter, they better have some pretty precise mechanism of manipulating this voltage so that they can get the desired voltage noise. And they have sort of two goals. And these are discussed more in our attacks. The first one is, okay, can we manipulate this voltage in some way that we can cause the device being charged, trigger some kind of voice command that can, you know, perform some kind of integrity attack? And second, you know, wireless chargers, they're known for being quite hot, quite toasty. Can we manipulate this voltage to disable some kind of protection and, you know, burn the device or nearby objects? Let's talk about some of the weaknesses in our system that the attacker might exploit. First, we have this connection between the cable and the wireless charging coil. And this is where they might inject, you know, some mechanism to affect the voltage. Second, we have the connection between the charging coil and the receiving coil. So that's when, you know, you put your phone on top of some puck. There's some communication going there to make sure you're actually getting charged. And through this Qi packet protocol, you know, you can make sure, okay, I'm not overcharging, I'm not undercharging, when to stop charging, or if like, you know, something that's not a phone is on top, let's make sure we don't like charge that. So let's talk about a little bit about how the attack is done. And it turns out that a lot of it is done by exploiting this Qi charging specification. First, we take the power adapter, we manipulate the voltage. Next, we cause some kind of electromagnetic interference. I'm not in EE, so I'm not super clear on what this was. But effectively what the paper describes is, okay, we can modulate this power signal between the charger and the device using some kind of voltage noise through the cable. And in fact, by modifying it in this way, we can affect a controller within the charger to send some malicious Qi messages that can compromise our device. So here is a diagram that the paper illustrated. As you can see, we have some adapter. We have this kind of reddish segment. Maybe the attacker is modulating the voltage here. And then that communicates throughout the stack. And ultimately, we affect the device through a number of microcontrollers. So finally, we realize there's this one major weakness in the system, and it's really this Qi message system. You know, we have our voltage. If we can change the voltage but not send Qi messages, then we're safe. So what if we just remove the chi messages from the equation? That's kind of the naive solution that, that we might come up with. And it turns out that that's not, super practical, and that's because that these chi messages turn out to be quite important. They're an in-band communication mechanism between a wireless charger and a device, and they control, quite importantly, if power is sent. You can imagine if I take my phone and put it on some puck, if I'm at 100%, I don't want, to be overcharging, that compromises, my battery and things like that. So these chi packets control dynamically if we send power from the puck to the device and stop it when it's fully charged. Moreover, we can imagine you put some metal device. We don't want to put some metal device and have the charger start, heating up the metal device and causing some problems. So that's what the paper describes as foreign object detection. So these chi messages, they're quite important. But it turns out that both of these important mechanisms can be exploited in certain ways to cause some of the attacks that Michael is just going to talk about.
Right, and now we get into the real fun and scary stuff, right? So we were talking about how with these messages that actually we can control the voltage, which means we can actually also induce sound into the microphone of the phones. So what we end up seeing is this behavior where what's happening is we're able to control Siri and Google Assistant, for example, to execute some commands. Like, for example, we can launch apps, we can make phone calls, control the camera, we can even browse websites. I mean, I think it would be pretty scary if like the CIA comes knocking on your door asking, hey, why are you browsing websites about how to make nuclear bombs? And you have to explain to them, oh, no, that wasn't me. That was my wireless charger. But what the authors found out was, okay, there's this 3 centimeter range limit, which of course we can extend to 10 centimeters with a Renesas power receiver. But in general, this 3 centimeter range isn't actually an issue because, right, you're going to put your phone to charge wirelessly and leave it be, and then we can start messing with it. We mentioned on Monday also how this idea of you can have a super effective attack, but if you actually have to be there in person to mess with the hardware, it's not actually as effective. Still, I think that this has a lot of merit to it. So here's a really interesting diagram. Like if you look at the original voice spectrogram and the input voltage spectrogram, it's almost identical, right? It's kind of scary. We can just basically recreate your voice and play it into the microphone of the phone. And it's just like, okay, this is you. But that's a massive attack on your integrity, basically. And oh boy, this one is even more dangerous. Cooking your phone, steamed phone. But basically, there's this idea where we can actually sabotage legitimate chi messages and packets, and we can actually also inject fake ones to just continue telling it, okay, keep charging, keep going, don't charge, don't stop charging. And what ends up happening is we have this behavior where your phone goes beyond charging 95 degrees Fahrenheit, which is the safe limit. It goes beyond 126 degrees Fahrenheit, where it's supposed to just shut down, and it keeps going until finally either your battery just completely going to malfunction or your phone's going to blow up. I mean, if you remember earlier in this quarter, we actually talked about the pager attacks and the explosions, right? Well, in that case, what ended up happening was they kept charging the device until they actually exploded the battery, which was also tampered with. Well, similarly, while the battery hasn't been tampered in this scenario, it still can explode. I mean, if you have a lithium battery, that can be pretty dangerous. So I think there's some real merit to this, and it's actually quite dangerous. This has to be covered for eventually. Okay, and here's an image, for example, of what actually it looks like when this attack is happening. I mean, you can see 178 degrees Fahrenheit. Again, to mention the pager attacks, I think one caveat to this is the person would probably feel that their device is getting super hot and know something is wrong, just like with Hezbollah, who ended up throwing away their pagers in some cases. So there is that caveat, but still, the fact that this can happen in the first place is quite dangerous. Right, so the authors did propose some solutions, but in our opinions, they're not super reasonable. The first one is, okay, use a DC converter in order to filter out the noise. Well, sure, that probably would work, but I mean, we're increasing the cost, there's gonna be strain on your battery, there's additional hardware involved, and it's just not very reasonable in all cases. Well, sure, they introduced a second solution as well. What if we just monitor the voltage, you know, have something that detects abnormal activity, tries to catch it and stop it? Okay, you can do that, but again, that's a high complexity implementation, still going to increase cost. Are you really gonna implement it on low cost and low power devices? It's still not reasonable, to be fair. So the ways that the authors did their test, of course, was in a very controlled environment. I mean, they had to be careful. They tested both iPhones, Google devices, Pixels, you know, stuff like that. And basically, in the attacks, they did have to introduce like this intermediary device, right? Which again, for this presentation, is a massive caveat to this entire attack. But still, if you have a way to basically distribute these modified devices like with the pager attacks, then it's still a very reasonable and dangerous attack that needs to be covered for. And eventually, we need to basically figure out how can we stop, modify the Qi protocol or introduce some type of middleman to stop this from happening, which actually leads me into the discussion questions. So I'm asking basically, do you guys think that there are better alternatives than the solution that was proposed? I mean, there was the converter or the monitoring, but surely there's got to be something better, right? Does anyone have any ideas? Yeah?
I had a question for like how small is like the voltage like equipment that you need to like modify the charger? And we're like, because I was thinking of like the fake USB cables that like could like hack your phone, but I'm thinking like how small is this like attack?
Oh, I mean, it doesn't have to be large at all. Yeah, it's just basically you either have to modify the existing wireless charger or introduce something in the middle, just like anything that can basically intercept the Qi messages and like just mess with it.
Yeah, so the authors are saying, okay, so you have some power brick that's attached to the wall and some cable. Okay, let's switch out the power brick for some other power brick. So it's a relatively covert attack because, I mean, they're expecting the power brick to be there. You can introduce some kind of microcontroller inside the power brick and suddenly your voltage is messed up. So that's kind of,
something that you can manipulate the voltage at the
Yeah.
wheel. So either like, you know, you change the cable to some other cable. So there has to be something active that can dynamically change.
Yeah.
This doesn't solve all of the problems, but why not just have like some sort of heat-based like circuit breaker? That would be kind of a cheap alternative to prevent it from at least heating up your phone to like 170 degrees or whatever.
Totally, yeah. I mean, that would be a good idea to at least stop the overheating attacks, which I think would probably be the bigger issue, right? We don't want to cause physical danger. Yeah, what's up?
Yeah, I mean, going to the overheating attack as well, maybe you can have like a software module in your phone, like, because obviously it does have charge, right? So, or maybe it could be battery powered as well, but it like the text like, oh, we're having a lot, and just like sends out like alarm, like, I don't know, like an alert on your phone, like loud beeps, and then you know that something's going wrong, right?
Yeah, totally. That would be a
I think that would strongly depend on someone being nearby to, you know, take the phone off the charger.
That's true, I guess so. We talked about how this happened with the pager attacks, right? But in general, does anyone else have any ideas about how attackers could probably exploit these vulnerabilities beyond just smartphones? Yeah.
I'm not totally, this is not like the discussion, but like, is this attacking the charger or like the components in the, like, is this attacking the charger's components or the phone's components or both of them or what?
Okay, so the attack is, the threat model supposes that, okay, the attacker wants to affect the phone in some way. But the mechanism to do that does not affect the phone. The mechanism to do that changes like the power adapter or the cable or in some way modulates the voltage. So by manipulating the wireless charger in some way, we're able to attack the phone.
I think you had the good picture at the beginning, where you go.
Yeah, this one.
Yeah, this. So that red line is like where the attack happens. So
yeah, so like
somehow you
this-
change the voltage there, and then everything else is just automatically.
Yeah. Back to the discussion question.
Any more questions or discussion or anything? I'll probably go through the last question quickly. I mean, does anyone have any ideas for how the Qi standard maybe could be modified? Because I brought up in the first question, for example, there has to be better alternatives, right? Well, one alternative is what if we make the Qi protocol better? Does anyone have any ideas for that? Well, probably if we made some better like authentication or encryption method, that would be a good solution, right? I see we're running low on time, so I think we're gonna stop here unless if anyone has questions. Perfect, thank you.
So,
we don't have much time, so I'm gonna let you guys go, but generally, just quick feedback about the presentations. Few things, don't forget to upload your slides to that shared folder for the presenters. Others, don't forget to submit your reviews. You have until next Wednesday. And whoever was not present in the class, so watch the videos and submit your reviews as well. And in terms of presentations, were great. We may need to be a little bit more efficient on time, but I think since we had good discussions, I didn't really try to kind of stop it. That means that we might need to kind of like shorten the lecture part of the class for those presentations, but we have 4 of these presentations, so we should be good. The rest we can just continue the regular lectures. Is there any final questions? All right, good. See you guys next week.